Hi there, welcome to lecture 15. This is on section 4.5 on our trig derivatives. So in sections 4.1 through 4.4, we worked on all of our derivative rules with polynomials. So we know how to manage all of our operations. So now we want to start adding in some of the fun functions. Okay, so in section 4.5, we're going to add in trig functions. So we're going to start with sine and work our way up. So we don't have any rules for sine of x, okay? Keep in mind, this is not sine times x, right? Sine does not exist without the x next to it. So this is one entire thing. Sine of x is a whole thing all on its own, okay? You can't just have sine without the x. And so we don't have any rules to work with here. When we don't have rules, we go back to the drawing board. We go back to what we know, which is the definition of the derivative. So we know that f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. So that's what we're going to do here. So if we apply that to our sine function, then we're plugging x plus h into our sine function. So the limit as h goes to 0 of sine of x plus h minus the sine of x all over h. Okay, now typically when we get into this situation, we want to do something, some kind of algebra trick, and then we want to factor. And right now, the sine of x plus h and the sine of x are not like terms, and I cannot factor them out. I also cannot distribute the sign to what's inside the argument. It doesn't work that way. But there is an identity that we can use. We know that the sine of a plus b is as follows. Sine of a times the cosine of b plus, and I'm going to run out of room. Let me move this over. Sine of a cosine b plus the cosine of a times the sine of b. So we can use that here where our a is x and our b is h. And oh, I'm slanting that pretty good. So let's see if we can do a little better. So this is the limit as h goes to 0 of sine of x cosine of h plus the cosine of x sine of h. So that's what replaces. So this one replaces this one using that identity, right? And you can see kind of how I did that. The a is the x, the b is the h. And then you're subtracting the sine of x. So minus sine x. And all of that is over h. Okay. Now, if I look at this first term, the sine x cosine h, and the last term, those both have a sine x. So I'm going to put them together and factor out the sine. So we have the limit as h goes to 0. And I'm going to bring the sine x out in front. And so after that, I have the cosine of h minus 1 when I factor it out. And then the term in yellow there is still there. So plus the cosine of x times the sine of h. And that's all over h. Okay, at this point, notice that my limit involves h's and not x's. So things that have x's don't have the limit applied to them. So what I can do is I can kind of start to separate things. So I'm going to split it right down the middle. I'm going to split my addition, and I'm going to give them both limits. So the limit is h goes to 0. I have the sine of x, which does not rely on the limit at all, but I have the cosine of h minus 1 all over h. Plus, I have the limit as h goes to 0, so I'm giving each piece its own limit. The cosine of x times the sine of h over h. Okay. Now, one last thing I want to do so you can see what's going on. I'm going to take the part that has the x in it and move it outside. So this is the sine of x times the limit as h goes to 0. And I'm going to factor out a negative here and make this negative 1 minus the cosine of h all over h. Plus, we move the cosine of x outside of this limit. And then we have the limit of sine of h all over h. Okay. Now, why did I do that? Well, I did that for a reason, because these limits right here are our special limits back from a few sections ago in chapter 3, in section, I believe it was 3.4. So what we have here is the sine of x times this limit is 0. That was one of our special limits. Plus, then I have the cosine of x times this special limit was 1. So this is times 1. And when you take the sine times 0, that's 0 plus cosine times 1 is just cosine of x. And so what we know is that the derivative of sine x is just cosine x. So a lot of work to get to a little derivative that we can use. So moving forward, you don't have to know how I got that. You can follow it if you like, but you need to know that the derivative of sine is cosine. Okay. Same thing for cosine x. If we do exactly the same thing, we're going to have the limit, f prime of x, let's use good notation first, is the limit as h goes to 0 of cosine of x plus h minus the cosine of x all over h. And the identity that we want here is the limit as h goes to 0. The cosine of x plus h is the cosine of x times the cosine of h, and then minus the sine of x, sine of h. Okay, so again, that replaces the cosine of x plus h. And then I also have minus cosine x on the end. All of that over h. And I'm going to use the same procedure. So I'm going to take this one that has a cosine and this one that has a cosine, put them together and factor the cosine out. So this is the limit as h goes to 0. And I'm going to take the cosine of x away, and I will have left the cosine of h minus 1 minus sine of x, sine of h. Everybody divided by h. So from here, we're going to divide things up. So I'm going to have the cosine of x times the cosine of h minus 1 all over h, minus this time the sine of x times the sine of h all over h. Okay. And if you pull those out, this is the cosine of x times the limit as h goes to 0 of negative 1 minus cosine h all over h, minus the sine of x times the limit as h goes to 0 of sine of h all over h. Okay. We know that this one is 0, so this whole first term goes away. We know that this one is equal to 1, and so this just becomes negative sine x. And so our derivative of cosine is negative sine x. Okay. And those two are the most difficult because those we have to go back to the limit definition of the derivative. But now that we have the derivative of sine and cosine, we can use that to our advantage with the other 4 trig functions. So if we look at tangent x, what I can do is I can use an identity to rewrite the tangent of x as sine of x over cosine of x. And now I know each of their derivatives. So I can use a quotient rule here to find the derivative. So the top is sine x, and up above we said that the derivative of sine is cosine. The bottom is cosine x, and we just said that the derivative of cosine x is negative sine x. And so we can put the derivative, the f prime of x here, all back together using our quotient rule. So top prime bottom would be cosine times cosine, which is cosine squared, minus sine times negative sine would be negative sine squared, all over the bottom squared, which is cosine squared. When we simplify this, we add the opposite, and that becomes cosine squared plus sine squared, and we have an identity that says sine squared x plus cosine squared x equals 1. So I can replace the numerator with 1 over cosine squared x. And 1 over cosine we know is secant, so we can write this as secant squared. So we're going to say that our derivative for tangent is secant squared. Now this is one that I would expect you to be able to do. I would expect you to do exactly what I just did. Rewrite tangent as sine over cosine. Use the quotient rule to show that the derivative turns out to be secant squared. Okay. Same thing for cosecant. So cosecant is the cosine of x divided by the sine of x. So I'm setting up my quotient rule, only this time the top is cosine. And the top prime is negative sine x. My bottom is sine x. And the bottom prime is cosine x. So when I put my derivative together using the quotient rule, my top prime bottom is negative sine squared x. And it's quotient rule, so it's minus. And then we have bottom prime top, so that's cosine times cosine is cosine squared. All over the bottom squared, which is sine squared. If we factor out that negative, then you have sine squared plus cosine squared in the numerator. And just like last time, that becomes a 1. So we get a negative 1 on top and a sine squared x on the bottom. 1 over sine is cosecant, so this is negative cosecant squared x. Notice it's parallel from tangent, so negative cosecant squared. All right, and then we've got 2 more, cosecant x and secant x. So cosecant x can be written as 1 over secant x. Sorry, lied. Cosecant x is 1 over sine. I got the s right, though. Sine x. And this one, instead of doing quotient rule, you can do quotient rule if you like. I like to write this as sine x to the negative 1. And that way I can use chain rule. So the derivative here is negative 1 sine x to the negative 2. And the derivative of sine is cosine. That means I get a negative out front. The sine squared moves to the bottom. And the cosine is up top. Now what I'm going to do is I'm going to rewrite this. So I'm going to put the cosine of x over here, with a 1 here, and I'm put a sign underneath each one. And those are identities that I know. 1 over sine is cosecant x, and cosine over sine is cotangent x. So then our derivative for cosecant x is negative cosecant x cotangent x. And that's our derivative for cosecant. Same exact procedure is going to happen for secant x. So exactly the same thing here. So we're going to write secant as 1 over cosine. Or cosine x to the negative 1. So that when we take its derivative, we get negative 1. The cosine stays inside. New exponent is negative 2. Derivative of cosine is negative sine, so I'm multiplying by negative sine. And that means that these two negatives will cancel each other out. And I will have a sine x stays in the numerator, and the cosine squared moves to the denominator. And just like in the last one, I'm going to spread this out. I'm going to put a 1 here and a sine over here, and a cosine in each denominator. And this gives me secant x times tangent x. So those first two, for sine and cosine, I don't expect you to be able to generate the derivatives. But for the last 4, where we're using algebra and our identities, I do expect you to be able to recreate those derivatives. Okay. So what we want to do next is I want to just create a little cheat sheet chart for you so that you have everything you need. One spot to check things out. Let's put them in green. All right, so if your function is sine of x, up above we found that the derivative was cosine of x. If your function is cosine of x, the derivative is sine x, but it's negative. For tangent, we got secant squared, and cotangent was negative cosecant squared. The derivative of secant was secant x tangent x, and the derivative of cosecant was negative cosecant x cotangent x. Now notice, these are probably some things you're going to want to put on your note card for the exam, but notice that every trig function that has a co also has a negative. Right? And also notice that they sort of come in pairs. So cosine and sine look similar. Secant squared and cosecant squared in their structure look similar. And secant tangent and cosecant cotangent look similar. It's just the co of each other. So just some things to notice that help me remember my trig derivatives. In the guided practice, we'll start mixing these with some of our other derivative rules.